Let's now take a look at our common drain amplifier configuration. And remember that this configuration is often referred to as a source follower, and we'll see exactly why that is here in a little bit. So let's take a look at this relatively simple circuit here. We notice we have the same basic thing at our input. We have our biasing network of R1 and R2. We have this coupling capacitor, which is acting as a short circuit for AC signals, an open circuit for DC signals, and then we have our source, which is represented by this ideal VI, as well as some non-ideal input resistance RSI1. And now we have a source resistor, but no drain resistor. So we notice that our drain is connected to VDD, which is going to be signal ground. So our drain is at signal ground. And so that's going to come into play as we're looking at our small signal equivalent circuit here in a little bit. And the other thing we notice that we saw in our summary table is we still have our input at our gate, and now we have our output defined at our source as opposed to at our drain. So that's one of the key ways that we can tell this is going to be a common drain, or as it's also called, a source follower amplifier. So let's go ahead and start by looking at our small signal equivalent circuit. So we want to draw our small signal equivalent circuit just like we normally do. And so again, as some practice, what you could do is pause the video and try to draw this yourself before coming back to see what it looks like here. So a good starting point is always to draw out our three terminals. So we've got our gate, our drain, and our source. So gate, drain, and source. And so in this particular case, we said our drain is going to be at signal ground. So let's go ahead and let's not get rid of that, but let's put our signal ground here. We know, like normal, we're going to have that dependent current source, which is going to be flowing. Again, we can see that we have an NMOS because our source arrow is pointing outward, so our drain current is going to be flowing from the drain to the source. Between the drain and source, we're also going to have that small signal output resistance if we want to have sort of the most complete model. So this is going to be GM VGS for this dependent source, where our VGS is of course defined as this voltage between our gate and the source. Okay, so there's our transistor. So now we need to add everything else that we see in the circuit. So we see at our source, we have this resistance RS, which is between the source and ground. So let's go ahead and add that in here. So I'm going to go ahead and put another ground right now. So we've got an RS like that. On our input side, it's the same thing that we've seen before. We've got this parallel path of R1 and R2 from the gate to ground. Because this coupling capacitor is acting like a short circuit to AC signals in this small signal equivalent, we're going to draw that as a short. And then we have this series combination of our VI and our RSI. So adding all of those things on our gate side, so we have this RSI, and that's going to our gate. We also have this parallel combination of R1 and R2, which is between our gate and ground, so I'm going to connect that there. And then we had that VI, which is in series with the RSI up here. So this is our RSI. Let's go ahead and connect that before I forget there. And this was our R1 parallel R2. And so let's go ahead, and one more thing to add is our output. So we see our output is defined at our source. So this is our source voltage. So we could basically just say right here, between here and ground, this is our output voltage, V out. Okay, so this is a technically correct small signal equivalent circuit, but it's a little bit messy to look at and to work with. So what we can do if we want to clean this up and make it a little more user-friendly is we can basically flip this part up here down such that our two grounds are going to be at the same place. So let's come up here and say we're going to quote-unquote flip this down to put the grounds at the same place. And so at the same time, what we can do is we can sort of take this and we can sort of stretch it a little to the left and a little down such that this VGS isn't going to be going across this sort of diagonal gap, but rather it's going to be a nice horizontal gap. Again, we're not changing anything in the circuit or even in how we're representing the circuit. We're just drawing this diagram a little bit differently. Again, not drawing it as in changing connections or configuration, just how we physically draw it on the page. So if we do that, we're going to get an updated small signal equivalent circuit that looks something like this. So again, let me sort of come back up here so we can see we've just put those two at the same spot. So now our drain is going to be down here at the bottom, and we're going to have our source and our gate sort of up here on the top part. So that's exactly what we see down here. Our V out, notice, is still defined at the source. Gate input side, everything is the same there. So of course this is a little easier to work with than, a little easier to visualize than something like this. So let's define a couple more things on this circuit before analyzing a couple parameters of interest. So first of all, let's define our input voltage to the amplifier as this voltage across R1 parallel R2. So let's call this Vin. And so remember, that's because this RSI is some internal resistance of that input voltage. We can also define input and output resistances of the amplifier. So let's say we're looking into the amplifier here. It's going to have some input resistance R sub I. And if we're looking into the output of our amplifier from this direction, it's going to have some output resistance, capital R sub naught. And so again, it's very important to distinguish between the lowercase r sub naught and the uppercase r sub naught. The former is the small signal output resistance of the transistor, whereas the latter, the capital R sub naught, is going to be our overall output resistance of the amplifier. So again, important distinction there. Okay, so now let's set out to find some of those key parameters of interest. So let's start with our input resistance, because that's relatively easy. That's going to be the same thing as we saw in our other configuration, our common source configuration. So our input resistance, because we have this infinite resistance at our gate, we're going to have no effect from anything over here, and our input resistance is simply going to be this R1 parallel R2. So same as the common source, we're going to have Ri is just equal to R1 parallel R2, and again, sometimes we'll refer to that as R Thevenin. All right, that was relatively easy and painless. So now let's take a look at our small signal voltage gain. So small signal voltage gain, and again, note we've included this lowercase r sub naught. Of course, once we get our final equation, we could sort of adjust it if we assume that r naught is infinity, and we would get a simpler equation. Okay, so the basic idea, as we've seen previously, is we're going to look at our input loop, our output loop, use the VGS as sort of the bridge between the two, and ultimately get something that is just in terms of V out and V in. So let's start, in this case, on our output loop. So if we're looking at our output loop, we see we're going to have this current GM times VGS, which is going to go through this parallel combination. So let's go ahead and combine those into one resistor. That's going to make it a little bit easier, and it's going to have some voltage drop that looks like this. So in contrast to our common source amplifier, we see that that polarity is going to match up with the polarity for our output voltage. So we can say that our V out coming down here is just going to be equal to that current, which is GM times VGS, times the parallel combination of RS and lowercase r sub naught. And so let's call that equation 1 to be consistent with the notes. Now what we're going to do is we're going to go to our, we're still going to be looking here at, well, kind of a combination. Let's do a KVL around this path here. And so what we're going to do is we're going to, of course, be relating our V in to our V out, and then we can relate the V out to our VI. So what we see around that path is that we're going to have V in is equal to VGS plus V out. So let's come down here and write that from KVL. We have that our V in is equal to VGS plus V naught. And we just had this expression for V naught above, so let's go ahead and substitute that in. So we have VGS plus GM VGS times RS parallel R naught. Now we can rearrange for this and solve for VGS. So if we solve that equation for VGS, we have that VGS is equal to Vn divided by 1 plus GM times RS in parallel with R naught. And let's call this equation 2. Okay, so now let's go back to our input side and figure out what an expression is for that V in. So notice we still have this V in here that we want to get rid of, or rather we want to get it in terms of our VI. And so as we've seen previously, that's going to be relatively simple, just doing voltage division. So from voltage division, we can say that our V in, the input to the amplifier, is just going to be Ri divided by Ri plus RSI times the VI. And let's call that equation 3. And note again that this Ri we've defined up here above as equal to R1 parallel R2. Okay, so now what we're going to want to do is we're going to want to substitute 3 into 1. So let me write this and then we'll kind of step through the equations up there. So we're going to substitute, sorry, not into 1, 3 into 2 rather. And then we're going to take the result, and we're going to substitute the result into equation 1. So we're going to take this expression for Vn, we're going to put it here, such that we have VGS is going to be in terms of VI and some resistors and GM. And then once we have that VGS expression, so we have this VGS expression, we're then going to substitute that into our first equation. So then we're just going to have V out, and ultimately we're going to have this Vn that sort of track through all of those substitutions. And so glossing over the algebra and the processes behind that, what we get is our AV is of course going to be equal to V out over Vn, and that's going to be equal to, we're going to have Gm times Rs in parallel with R naught, and in the denominator 1 plus Gm times Rs in parallel with R naught, and that is going to be multiplied by that voltage divider ratio, so Ri divided by Ri plus RSI. So if you have any questions about the details of that algebra there, definitely let me know. But I think, it's not too big of a deal. We're really more focused on this end result here, and so let me bring that down a little bit. Okay, so a couple things that we can observe from this. So we kind of already expected this, but we note that our voltage gain is greater than 0. In other words, it's positive. And so what that means is that our input and output are going to be in phase. So input and output are in phase. And so that's in contrast to with our common source. We saw we had a gain of negative something, which of course corresponds to the input and output being 180 degrees out of phase. But in this case, our input and output are going to be in phase. The other thing that we can note is that our AV is always going to be less than 1. So AV for this case is always less than 1 or less than unity. Sometimes you'll hear that stated that way. And so we can recognize that by saying, we have this term here, which is the same as this here, this term here, which is the same as this here. So if we have, of course, this one term, that's going to make this denominator a little bit bigger than the numerator. This RSI, which ideally is going to be 0, but in practice is never going to be 0, is going to make that denominator a little bit bigger. So that's always going to be less than 1, but what we're going to see is typically it's going to be close than 1. So maybe it's going to be something like 0.95 for our voltage gain. So the question then becomes, why is this useful? So why is this configuration useful? And so we're going to come back and we're going to answer that question in the next video when we look at the third parameter, which is our output resistance of the circuit. And we are going to see that it is useful in certain cases to use this configuration.